Welcome back, my dear friends. So, do you remember what all things we have discussed yesterday? We have actually touched upon analytic functions, and how do you check whether a given function is analytic or not? Actually, the method is to check whether the function is independent of z bar. So, once you are able to write your fz independent of z bar, then you can say the function is analytic. But that was not a convenient method. So, we have also seen another method, an alternative method to check whether a given function is continuous. Do you remember the theorem on Cauchy-Riemann equations? So, it says that if your function is analytic, it should satisfy the CR equation. So, how do you check whether a given function is analytic? So, you have to find the first order partial derivatives of the function f of z and check whether the CR equations are satisfied. Also, together with that, you have to check one more condition, that is the continuity of all the partial derivatives of first order. If both the conditions are satisfied, then you can say that the given function is analytic. We have also seen the CR equations both in Cartesian coordinate system and also in polar coordinate system. So, if I give you my fz in the Cartesian coordinate system, that is in the variables x and y, you use the CR equations in xy form, or else if it is given in r theta form, that is the polar form, you use the CR equations in polar form. We have also seen some of the problems in both the cases. So, let us see some more results. If your function f of z is analytic and suppose the modulus of f z is a constant, in that case your f of z is also a constant. The proof is very simple by using the CR equations. The same is the case when your f z is analytic and suppose the amplitude of f z is a constant, then your function turns out to be a constant. So, the same case happens if either the real or imaginary part of your function is analytic. So, now suppose I give you a function and ask you to prove that it is not differentiable at some point, but you can see that the CR equations are satisfied. Let us see one such function which is given by f of z is equal to x cube minus y cube by x square plus y square plus I into x cube plus y cube divided by x square plus y square. So, your real part of the function f of z is x cube minus y cube by x square plus y square, and the imaginary part is x cube plus y cube by x square plus y square. So, if I have to evaluate check the differentiability at z equal to 0, that is the origin, how do you do it? We can do it only by the definition of partial derivatives, that is the limit definition of partial derivatives. So, if I have to find dou u by dou x, you go by the limit definition. So, what is the definition for dou u by dou x? It is limit x tends to 0, u of x 0 minus u 0 0 by x minus 0. So, which is obviously x minus 0 by x as limit x tends to 0, which will give you 1. So, in the same way dou u by dou y, if I go with the limit formula, gives me limit y tends to 0 minus y minus 0 by y, which is minus 1. In the same way we proceed to find out dou u by dou y and dou v by dou x, which will give you respectively minus 1 and plus 1. So, you check the CR equations, you can easily see that ux and vy is equal to plus 1 and uy is equal to minus vx, that is minus 1. So, here clearly the CR equations are satisfied at the origin, that is z equal to 0. But you can see how the function is defined. Your function is u plus iv when z not equal to 0, where u is x cube minus y cube by x square plus y square and v is x cube plus y cube by x square plus y square, and at z equal to 0, that is at your origin, the function is taking the value 0. So, even though the function is defined in this manner, you can see that the CR equations are very much satisfied here. So, suppose I have to show that it is not differentiable at 0 0. So, I again go with the limit definition to find f dash 0, and you can see that f dash 0 is nothing but the limit z tends to 0 of f of z minus f of 0 by z. So, if I substitute the value of the function, what do I see there? So, I get the expression f dash 0 is equal to limit z tends to 0 x cube minus y cube plus I times x cube plus y cube divided by x square plus y square into x plus I y. So, how do I prove that this limit does not exist? In the previous session, when we have discussed the analytic function, while discussing the differentiability definition, I have already mentioned that if you have to prove that a limit does not exist in the complex case, it is enough for you to prove that the limit is different along different paths. So, here I proceed by choosing some path for z to tend towards 0, that is the origin. So, let us choose a general path now, y equal to mx, which is obviously the linear equation, it is a straight line. So, you get your f dash 0 as limit x tends to 0 x cube into 1 minus m cube plus I times x cube into 1 plus m cube divided by x square into 1 plus m square into x into 1 plus I m. So, what do I get as a result? See, you are finally getting an expression which is independent of x and it depends on your parameter m, that is the slope of the straight line. So, what can you conclude now? Your f dash 0 is a function of the parameter m that you have chosen, that is 1 minus m cube plus I times 1 plus m cube divided by 1 plus m square into 1 plus I m. So, since the limit depends on the path, it is not unique and hence f dash 0 does not exist. The CR equations are not only sufficient for proving a function to be analytic. Clearly, this is depicted by the example we have seen just now. Let us see the definition of a harmonic function. Suppose I have a real valued function phi of x y. I say the function is harmonic in a domain D if all of its second order partial derivatives are continuous in D and if each point of D satisfies dou square phi by dou x square plus dou square phi by dou y square is equal to 0. This equation is known as the Laplace equation. So, what are the conditions required to prove a function is harmonic? So, once I have a function in two variables, say x and y, I need to check whether the Laplace equations are satisfied. For that, you need the second order derivatives of the function phi with respect to x and with respect to y. See whether uxx plus uyy or else phi xx plus phi yy in this case is 0. Together with that, you also have to ensure that the function is continuous. Both the first and second order derivatives of the function has to be continuous in the domain under consideration. Then you say a given function is harmonic. So, how is it related to the analytic functions, or else why are we discussing it under the topic analytic functions? So, let us see a theorem which gives you the connection. If f of z is equal to uxy plus I vxy is an analytic function in a domain D, then each of the functions u of xy and v of xy is harmonic in D. So, what does it say? If I have a function f of z is equal to u plus iv analytic, then both the real and imaginary parts of f of z has to be harmonic functions. So, once you have f is equal to u plus iv analytic, then you call the u and v, that is the real and imaginary parts of the function, as harmonic conjugates. So, the real and imaginary parts of a function f of z which is analytic is known as the harmonic conjugates. Given a function u of xy harmonic in say an open disk, we can find another harmonic functions vxy, so that u plus iv is an analytic function of z in the disk. So, clearly you know that V is called the harmonic conjugate of u. So, let us see one example. Construct an analytic function whose real part is u of x y is equal to x cube minus 3xy square plus y. So, first let us verify that this given function u is harmonic. So, for that we have to find the first and second order derivatives of u with respect to x and also with respect to y. So, what do you get dou square u by dou x square as? In this case your first order derivative is 3x square minus 3y square. So, your second order derivative is 6x. Now, dou u by dou y is minus 6xy plus 1. So, your dou square u by dou y square is minus 6x. So, you can clearly see that the Laplace equation is satisfied in this case. So, your dou square u by dou x square plus dou square u by dou y square turns out to be 0. Now, you can ensure that a harmonic conjugate exists for this. So, let us call it y, and since u plus iv has to be analytic, you know that the CR equations are satisfied for f is equal to u plus iv. So, you know that dou v by dou y is nothing but your dou u by dou x, that is 3x square minus 3y square, and dou v by dou x is minus dou u by dou y, that is 6xy minus 1. So, let us integrate dou v by dou y with respect to y, keeping x as a constant. So, your integral becomes 3x square y minus y cube plus some function of x, because you are partially integrating this function v with respect to y by treating x as a constant. So, to find out that function in x, what do? We differentiate this function with respect to x. Dou v by dou x is 6xy plus the derivative of that function x. So, if we compare it with the second equation which you have obtained by comparing the CR equations, you get that 6xy plus this derivative of x, the constant which can be a function of x, turns out to be what? Minus 1. So, dou theta by dou x, as we have called this function as theta of x, turns out to be minus 1. So, integral is nothing but minus of dou x, which turns out to be minus x plus c. So, now what is your v of x y? V of x y is 3x square y minus y cube plus a constant of integration. So, if you are given a function u which is harmonic, you can always find a conjugate of it such that u plus iv is analytic. So, you can proceed in this way to find v. So, what is your function f of z now? I have given you only u of x y initially. So, my f z is now x cube minus 3xy square plus y plus I times 3x square y minus y cube minus x plus c. Now, suppose my f z is given in the polar form, that is, instead of x and y, I give you the function f of z in r and theta. To check whether the function is harmonic, the real and imaginary part of the function is harmonic, I have to use an alternate equation for the Laplace equation in Cartesian coordinate system. That is the Laplace equation in polar form, which is given by dou square phi by dou r square plus 1 by r dou phi by dou r plus 1 by r square dou square phi by dou theta square is equal to 0. So, when I give you a function in the polar form, you check whether the Laplace equation in the polar form is satisfied together with all the partial derivatives of the first and second order to be continuous with respect to r and theta. Now, suppose I give you a function and ask you to prove that it cannot be the real and imaginary part of an analytic function. So, I give you a function in x and y and I ask you to prove that it cannot be the real part of an analytic function. So, how do you proceed? So, whenever the function has to be the real or imaginary part of an analytic function, we have seen that by the theorem it has to be what? It has to be harmonic function. So, whenever I give you a function and ask you to check whether it can be a real part or it can be an imaginary part, the only thing you have to check is whether it is harmonic. So, whenever it has to be the real or imaginary part, it has to be an harmonic function, that is, it has to satisfy the Laplace equation. In the same way, I take two functions, say for example u and v. Both the functions are harmonic. Okay, that means u also satisfies the Laplace equation. All the second order derivatives of partial derivatives of u are continuous, that means u is harmonic. Again the same is the case with v. The partial derivatives of both the orders are continuous and also v satisfies Laplace equation. So, does it ensure that u plus iv is analytic? No. You have to check the condition, that is the CR equations, to ensure that u plus iv is analytic. So, just by joining two functions which are harmonic in the form u plus iv will not give you an analytic function. For that, CR equations has to be satisfied. So, whenever u is harmonic, there exists a harmonic conjugate for u. In the same way, whenever I have another function, say v, which is harmonic, there will be a harmonic conjugate for v. Okay, both of them should match, then only u plus iv will be an analytic function. So, we can easily understand what I have explained through an example. We take two functions, u is equal to x square minus y square, and you can see that this is a harmonic function. So, let us easily quickly check it. So, uxx is 2 and uyy is minus 2. So, your Laplace equation is satisfied for u, uxx plus uyy is equal to 0, and easily you can see that the functions, the partial orders, the partial derivatives are continuous. For both the conditions are satisfied and hence u is a harmonic functions. So, let us take another function, say v, that is minus y by x square plus y square. Let us check whether this is also harmonic. So, vx is nothing but 2xy by x square plus y square the whole square. So, the second order derivative is x square plus y square the whole raised to 4, x square plus y square the whole square into 2y minus 2xy into 2 times x square plus y square into 2x. So, this will be reduced to 2y into y square minus 3x square divided by x square plus y square the whole cube after cancellation. So, your second order derivative of v with respect to x is this. So, now let us see what is vy and vyy. So, vy is x square plus y square the whole square So, x square plus y square into minus 1 plus y into the derivative is 2y. So, this is nothing but y square minus x square by x square plus y square the whole square. So, now we take the derivative once more, vyy into 2y minus y square minus x square into 2 times x square plus y square into 2y. So, again you can see that this also simplifies to nothing but 2y into 3x square minus y square divided by x square plus y square the whole cube. So, from these two equations, say I call it 1 and 2, you can easily verify that Vxx is nothing but minus of Vyy. So, that is the Laplace equation is satisfied by V also. So, we have earlier seen that it is satisfied by U, now we see that it is satisfied by V. So, what does it imply? It implies that both U and V are harmonic functions. You can easily verify whether it is continuous. You can see the only problem lies for the function v is at the origin. The Laplace equations are satisfied and hence your function u and v are separately harmonic. So, can you now conclude that you are having two harmonic functions in hand? Can I simply write u plus iv and say that it is an analytic function? No. For that you need to check whether the function is satisfying the CR equations. Since all the first order derivatives are also here, you can easily verify what is ux and what is vy. Are they the same? No. Your ux is 2x and uy is minus 2y. So, your ux does not match with your vi and uy is not equal to minus vx. That means the CR equations are not satisfied and hence u plus iv cannot be analytic. So, it does not mean that any two harmonic functions when written as u plus iv will be an analytic function. So, in the same way you can also do problems using the Laplace equation and check whether they are harmonic or not. And also suppose if u and v both are harmonic function, you can easily verify that u into v, the product of two harmonic functions, are also harmonic. That is a result. The proof is very simple, because whenever u is harmonic, you have the Laplace equation for u. Whenever v is harmonic, you have Laplace equation for v. Now, I have to just prove that u into v also satisfies the Laplace equation. So, let us quickly see this result, how to prove that u into v is, so that is u is harmonic, v is also harmonic. You have to prove that u v is harmonic. So, u is harmonic will give you an equation u x x plus u y y is equal to 0. This will give you v x x plus v y y is equal to 0. So, here what do I prove? I need to prove that u v of x x and u v of y y should be 0. So, what is u v of x? U v of x is, you know, since it is product, I will have to apply the product rule. So, it is nothing but u x into v plus u into v x. So, I differentiate it again with respect to x to get the second order partial derivative. So, I get again I will have to apply product rule both for these two functions, because it may contain x again. So, I have u x x into v plus u x into v x plus u x into v x plus u into v x x. So, I have v into, no, we will proceed. So, okay, u x x into v plus u into v x x plus 2 times u x into v x. Now, in the same way I proceed to find u v, the derivative with respect to y. So, it is u v y plus u y v. So, if I go for the second order derivative, what do I get? I get u v y y plus 2 times, I can quickly write it because it is going to be similar. You are replacing your x with y, u y into v y plus you will get u y y into v. So, I have two equations, 1 and 2 here. So, whenever your function u is harmonic, so I should have the condition u plus iv is analytic, then only you will be able to prove this result. So, whenever your u plus iv is analytic, that means u and v are harmonic conjugates to each other, then the product u into v will also be a harmonic functions. You can, what you can do is you can just add these two equations So, you know that uxx is nothing but minus uyy and vxx is nothing but minus vyy. So, if I substitute it here, this two equations when I add up becomes 0, whereas this part 2 times ux vx and 2 times uy vy becomes 0 because your function u plus iv is analytic. So, whenever my function u plus iv is analytic, your CR equations are there. That means your ux is equal to vy and uy is equal to minus vx. So, this will ensure that 2 times ux vx and 2 times uy vy becomes 0. So, if I add the left hand side, the right hand side becomes 0, that means uv also satisfy the Laplace equation. So, once it satisfies, and you know, you can easily see that the partial derivatives are continuous. Why? Because u and v are harmonic functions. So, all the first and second order derivatives of u and v are continuous. So, for u v also it has to be continuous. So, whenever u and v are harmonic conjugates to each other, then the product is also a harmonic function. So, let us quickly conclude what we have learned in this session. We have seen the case where if a CR equation are satisfied and still the function is not differentiable at some points. So, this can clearly be explained by the term or the definition of analytic function, because we know that analyticity is a little bit more to differentiability, because if I have the function to be analytic at a point, it has to be differentiable in the neighborhood of that point. After that, we have seen the harmonic functions, and you know now how is it related to analytic function. Both the real and imaginary part of an analytic function is harmonic, and also if it is given in the polar form or the Cartesian form, in order to check whether a given function is harmonic, you need to check the Laplace equation. So, we have seen the equation and we have seen some problems how to prove a given function is harmonic, and still having two harmonic functions in hand, you cannot have u plus iv analytic. So, let us continue with a method of finding an analytic function f of z given any of the harmonic function or else the conjugate. If I give you a function, how do you find its harmonic conjugate? Not by using the only method of analyticity or else the property of analyticity. So, let us continue with this in the next session. Thank you for watching this.